Good evening. Hello. Good evening. Good evening. Dattatreya, Varshita, Navina, Saurav Mahapatra. Welcoming to Contact Session 3. At 4:15, there are only 4 candidates. So let's just wait for another 3-4 minutes. Is it okay?
Okay, sir.
Yes. So, okay, then I think it's not improving still much, but okay. So in this session, we will continue to have more properties of determinants, and we'll also again reinforce and recapitulate solving system of linear equations, maybe 2 in number or 3 in number, using Cramer's rule, even though it was discussed in the last session itself, and continue to have finding inverse of a given square matrix using both Gauss-Jordan method, that is by reducing into echelon form, the augmented matrix in such a way that you will start with the AI instead of not AB, where B is any constant matrix or column matrix, column matrix of constants. But here you will have the I unit matrix, so that after the transformations are taken place, are done, you will come to know the right hand side is made to be I A inverse. And that right hand side, the end, is the required inverse of the given matrix. This is by Gauss-Jordan method, named after two famous mathematicians. And finally, of course, you can also have a recapitulation of what you have done in your school days, finding inverse of the matrix using determinants themselves. So with this preliminary note, let me share in detail what is in store for you in this session. As I mentioned already, under this main caption in part 1 of linear algebra, we still have matrices and determinants and linear systems and inverse of a matrix by Gauss-Jordan method. So look at, already we have discussed in detail about a determinant. It's nothing but determinant of a matrix where you will be replacing the matrix symbol of ordinary brackets or square brackets by two parallel lines, so that it enables you to simplify or expand by any row or column to get a simplified values. That is, the value of the matrix is determined. So it's called a determinant of a matrix, or we call it generally determinant, which you can say if A is a matrix, then determinant A, determinant B, determinant C, you can write DET followed by the matrix symbol. Or you can simply write capital D to stand for determinant. So here, of course, you have some kind of generalization. What is D? How do we multiply? And what are these C, etc. that you are going to see when there is an illustration, you'll be able to exactly understand. See, for n equal to 1, if that is, if the order is 1, that is one element 1 by 1, then D is just the element A11, which is the first row, first column. For n greater than or equal to 2, what is a D? It is the expansion through any row or any column. So that is the meaning here. Of course, you have a notation involving capital C, which stands for cofactor of elements of the matrix. So if you just look at this way, Cjk equal to minus 1 power j plus k mjk, where m stands for minor. Already the term minor I have taught to you in the last session that it is the determinant obtained by eliminating the corresponding row and column of the element in question, whose minor you are finding and whose cofactor you are finding. So what is the difference between these two? You are going to see. So look at where mjk is a determinant of order m minus 1 because it gets reduced. So when you are having a matrix of order 3 by 3, and when you find minor of any element, say in the first row, first column element A11, you get a 2 by 2 determinant. So naturally, if the original determinant is of order n, a minor of any element will definitely be of order n minus 1, namely the determinant of the submatrix of A obtained from A by omitting the row and column by the entry of the entry AJK. Okay. The jth row, AJK, you know, jth row and kth column. If you say AIJ, ith row, jth column. Look at So once again, we will re-emphasize that MJK is called the minor of AJK in D and CJK the cofactor of AJK in D. Now, what's the difference between these two? You just see minus 1 power J plus K AJK MJK, and you have for J equal to 1 to N and for K equal to 1 to N. So you can have for rows and columns. That is, what is the meaning of this? When you have an illustration, you will definitely be able to understand instead of theoretical notation. You just see that. That's what exactly it means. The expansion of a third order determinant. Already you know very well that we can expand through any row or any column. So here, as I put it in the last session itself, let us uniformly expand through the first row, which you can take it as a common rule, which is easy for you to remember. But you are at liberty to expand through any row or column. But remember that when you do through any row or column, the signs, positional signs, that is very important. Positional signs of the elements are to be taken into account without failing. That's the reason why I suggested to you to have the expansion through the first row, which by practice you will be able to do on without any mistake. In the sense, first you are taking the first row. When it is a determinant, you are taking into account that element multiplied by its minor, because you are expanding, you are simplifying, you are determining the value. And remember that each of the values of the rows and column has got its own positional value, starting from first row, first column, the sign plus. And it goes in alternate order as far as 3 by 3 is concerned. But for 2 by 2, you have to change, you have to see accordingly. Okay, anyway, it is alternate, plus, minus, and so on. So when you expand through the first row, here by 1, we don't mean the plus is optional, you know very well. It is not just the positional sign that we have not put here. If suppose you have minus 1 here, you will put minus 1 here. That means it is plus of the first element. Since it is 1, plus of 1 is simply 1. Suppose it is minus 1, plus of minus would have been minus 1 itself. That is, you will write the first element as it is, multiplied by its minor. What is its minor? MJK, corresponding row and column of the element in which it appears. You have the remaining 2 by 2 determinant. That's why when the order of the given determinant is of order n, its minor of each of the elements of the original determinant will be of order n minus 1. So here you will have a 2 by 2 determinant, isn't it? So this row and this column, if you eliminate means don't just remove it. Just understand that these two are not considered. So what is the remaining determinant? 6, 4, 0, 2 of order 2 by 2. Now, minus is the positional sign for the first row, second column element. Suppose here you have minus 3, it will become plus 3, isn't it? So here, this is positional sign of the first row, second column element, where the first row, second column element is only 3. Therefore, it is just minus 3 multiplied by its minor of the element 3. So you just conceal this corresponding row and column. You have to be careful about. So what is remaining? 2, 4, minus 1, 2. Plus 0 into, of course, you have 0 into, better you write. You know very well, 0 multiplied by anything is going to be 0, but still you write the minor. 0 into, what is remaining then? This is the corresponding row and column deleted. So you are left with a 2 by 2 determinant 2, 6, minus 1, 0. So once this is done, you go for expansion or simplification rather. So you know how to expand a 2 by 2 determinant. It is product of the principal diagonal elements. Principal diagonal. Again, here also it is plus of. So plus of the product plus 12. You simply put 12. Then you have the formula minus. Then multiply the secondary diagonal elements. It is 4 into 0, 0. Then you have outside minus 3 times. Now what is inside? 2 into 2, 4. Here you look at minus 4, which becomes plus 4, plus 0 into, you do the simplification, 2 into 0, 0, plus, because it is minus of minus 6, plus 6. Anyway, it is going to be 0, but do the simplification. So now it is 12 minus 3 into 8 minus 24 is minus 12. Well, this problem was already discussed, but still. Okay. So because what is important in all your calculations to determinants is the expansion. See that? So this is the expansion by the first row. The expansion by the third column is also shown here to be minus 12. So you can put your hands at verifying this by expanding through any column or any row. You should get the same value, minus 12. Determinant of a triangular matrix. So let us do it as before. But remember that it's a triangular matrix. What type of triangular matrix is this? Can anyone say? Having studied the types of matrices in the very first session, what type of matrix for which you have the determinant now? For matrix only we say triangular matrix. Of course, that's why we say here determinant of a triangular matrix. Let A equal to matrix minus 3, 0, 0, 6, 4, 0, minus 1, 2, 5. So what is determinant of this triangular matrix? Replace the matrix symbol by determinant symbol. That is two parallel lines, two straight lines. Isn't that? Minus 3, 0, 0, 6, 4, 0, minus 1, 2, 5. You just expand minus 3 into its minor. Why it is minus 3? It is plus of minus 3. Positional sign of first row, first column, it is plus. So you have to put plus. Then within brackets, you are supposed to write minus 3, which is nothing but minus 3, multiplied by its minor 4, 0, 2, 5. Then we have not written the remaining two simplifications because it's going to be 0. So minus actually 0 into the minor 6, 0, minus 1, 5 plus 0 into its minor 6, 4, minus 1, 2. You don't need to write because we know very well it's going to be 0. So the only simplification that you need to do is here minus 3 into 4 into 5 minus 0 into 2. That is minus 3 into 20 minus 16. Now, minus 16. Here, this is the determinant of a triangular matrix. I asked one question. What type of triangular matrix is this? Anyone? This was discussed in the very first session under the topic of matrices in detail, especially about special matrices.
Lower
Types of
triangular
matrices.
matrix.
Yes, come on.
Lower triangular matrix.
Very good. That's correct. It's a lower triangular matrix. As you see, zeros above the principal diagonal element. In other words, you are able to remember in this way that you have existence of elements below the principal diagonal elements. Therefore, it is a lower triangular matrix. Anyway, it is a triangular matrix. You got the answer, minus 16. Now, you just look at, there is one question. Inspired by this, can you formulate a little theorem on determinants of triangular matrices of diagonal matrices. Diagonal matrices we will discuss later. Okay. It is too early to talk about this, even though I think we were exposed to diagonal matrices also in the under the types of matrices. If you know, you can say, otherwise, at least as of now, you can say, can you formulate a little theorem on determinants of triangular matrices? That means the expansion of the determinant of a triangular matrix here definitely enables you to formulate a theorem or come to an understanding. What is it? By looking at minus 60, and there is a clue. Look at arrow mark. Minus 3 into 4 into 5. So the determinant of a triangular matrix is nothing but the product of its principal diagonal elements. Is it right? Whether it is a lower triangular matrix or its upper triangular matrix, now it's going to be simply the product of principal diagonal elements. Okay, right. Now we have seen enough by reducing the given matrix or its augmented matrix by doing row elementary operations. Whenever we say row within brackets, we can always put R column. So whatever is true for row is true for column also. So behavior of an nth order determinant under elementary row operation. So whenever we do elementary row operation, so if we have seen in reducing it in a triangular form, maybe upper triangular, lower triangular, or in general in echelon form, we have seen we have added a row with another row. We have multiplied by a constant elements of a row and added to another row, or subtract a row from another row. So these are elementary row operations where we have done practically. Now, now you can formulate out of those practical examples some of the results to be the properties. So the moment you see, you will be able to immediately give the answer. For example, what is the first one? Interchange of two rows, bracket within brackets, or columns, two columns, multiplies the value of the determinant by -1. Multiplies the value of the determinant by -1 means there is a change in sign. Suppose you have value of a determinant is say 8. You interchange any two rows or any two columns. So I don't need to repeat every time. Whenever we talk about any property for rows, it is true for its columns too, but not simultaneously. Okay, either rows or columns. So if you interchange any two rows, its determinant value will be changed. In the sense, if it was +8, it will become -8. If it is -8, it will be +8. We can just see an example. We just take a determinant. Let's say, for example, a simple determinant, a 2 by 2. Six -5. So -3. 4. Okay. So what is its expansion? 24 minus, be careful, -3 into -5. So it is minus of +15 or -15. 24 minus 15 is 9. Now, interchange the rows. Of course, if you are having a 3 by 3 determinant, you can interchange any two rows. Okay. So here are only two rows. So anyway, the question is interchange, isn't it? So interchange. Now you take -3, 4 to be the first row, 6 -5 to be your second row elements. Okay. What is this equal to now? -3 into -5, 15, minus 6 into 4, 15 minus 24 is minus. Isn't that? So interchange of two rows or two columns, okay, multiplies the value of the determinant by -1 means there is a change in sign. Addition of a multiple of a row to another row does not alter the value of the determinant. Addition of a multiple of a row to another row. Don't be misled here. You don't multiply the elements of the rows. Multiple of a row. That is, if you multiply a row by any common constant, that is called a multiple of a row, and add to another row by that is called another elementary row operation, it does not alter the value of the determinant. Okay, this you can see for yourself. You take a determinant. For example, you take the same 6 minus 5, and then you multiply by some common constant. Second row, for example, you get minus x 8. Okay, keep the second row fixed. Add this to first row and then do the expansion. You will get the same value. So addition of a multiple. This, of course, we have already done under elementary row operation, but we might not have checked it because that was not the property we were expecting it of. So you can check addition of a multiple of a row to another row does not alter the value of the determinant. Next, multiplication of a row by a non-zero constant C multiplies the value of the determinant by C. So if in any row or column, if you multiply the value, the elements of the row by a constant C, a scalar C, a non-zero constant. Okay, if you multiply, if you take C equal to 0, then it gives, this becomes, what will happen then? When C equal to 0, you get every value becomes 0. Okay, right. So multiplication of a row by a non-zero constant multiplies the value of the determinant by C. That's what is happening here. Suppose you have here minus 3, 4. Here you have 6, minus 5. And then you multiply by any one row or any one column by a constant common C. That is C equal to 1 or C equal to 2 or C equal to 3 or C equal to minus 3. And then what will happen? You find, suppose this determinant value is minus 9. And you take first row, for instance, you multiply by, say, 3, C equal to 3. Any one row multiplication of a row by a non-zero constant, say C equal to 3. You get minus 3, here 12. Okay. And second row becomes the same, remains the same, 6 minus 5. You expand, then you will get minus 27. That is 3 into minus 9. So multiplication of a row by a non-zero constant is nothing but C times determinant of the original determinant. Okay, right. Now, further properties. Transposition leaves the value of a determinant unaltered. What is the meaning? Determinant A is same as determinant A transpose. Transposition means A transpose. You will write A superfix T. Know that. Determinant. This is the first one, isn't it? It's the first one. What's the meaning? Because A transpose is, after all, obtained by interchanging either rows into columns or columns into rows. Uniformly, let us say, when A is given, A transpose is first row becomes first column, second row becomes second column, third row becomes third column. So now you find determinant values of A and that of A transpose. You will see that there is no change. They are one and the same. That's what it means. Transposition leaves the value of a determinant unaltered. Means if A, determinant A is the given determinant or determinant of a matrix A, and determinant A transpose means determinant of its transpose, then their values are the same. A zero row or column renders the value of determinant 0. Naturally. So if there is a row, even if there is one row or one column which are only zeros, then definitely the value of the determinant is 0 itself. And in this context, I would like to tell you one more thing is that if there are two identical rows, we don't say that two identical rows means if they are one and the same, they are equal, naturally the determinant value will be 0. Not necessarily that they are equal, even if they are identical. Even if they are identical, then you can see the value of the determinant to be 0. Okay, then I will show you an example. Not necessarily that any two rows or columns to be the same, but they are identical. Look at the word identical. We are going to see this soon. Still, then the value of the determinant is 0. In that case, also it is 0. I will show you. Now, proportional rows or columns render the value of the determinant 0. In particular, a determinant with the two identical, that is a meaning. So here we have the term proportional. That means you have identical in the sense here, you have elements of a row. Another row is, it is multiplied by elements multiplied by a constant of the elements of that row. So they are now identical because they are in the ratio, maybe 1:2. You know what is meant by the ratio 1:2. Suppose you have some elements 1, -2, 3. And if you have the other elements, the other row elements like 2, -2, 6. That is, they are in the ratio of 1:2. So the second row elements are proportional. That is, they are multiplied by 2 that of the first row elements. If so, proportional rows or columns means, so a determinant with the two identical rows or two identical columns has the value 0. Okay, I can show you an example for this. That suppose you take, just take it here. Let me see whether there is space in the next one or, yeah, here of course we have space. Just look at determinant A equal to -2 1 -4 3 4 6 5 -6 10. Okay, let us just now expand. -2 into, I straight away go for expansion. 4 into 10, 40. Minus of minus plus, you have 36. So 40 plus 36, 72. Sorry, 76. Formula minus 1 into, it's minor. 3 into 10, 30. Minus 5 into 6, 30. So you get 0. Then formula plus, you have -4. So plus of -4 is -4. Okay. So since there is a power cut, so therefore it will consume more power if the video is on. So I just switch off the video. I mean, the camera. Okay. So just listen to me now. Right. So here, -4 into what else is there? It's the minor. It is 3 into minus 6, minus 18, minus 20. So you have minus 38. Minus 38. So expand now. This is equal to minus 152 next is 0. Then minus 4 into minus 38 is plus 152. So it is equal to here to substantiate that property, you are able to see that you just see that first column and the third column. They are identical. Minus 2 into 2, 3 into 2, 5 into 2. So not necessarily they are the same, but the third column elements are in a multiple of 2 of column 1. So they are identical. Here C1 and C3 are identical. So anyway, if any two rows or any two columns are identical, then the determinant value is 0. Right. Now we will see some more properties here again. Determinant of AB is determinant A into determinant B. Determinant A not equal to 0 means there exists a matrix B such that AB equal to BA equal to I. So that what will happen, B is inverse of A. So whenever you have AB equal to I, that is, there exists a matrix B such that AB equal to BA equal to I. That is A inverse is equal to A inverse A is equal to I. So your B is nothing but your B is nothing but inverse of A. So whenever you have a matrix multiplied by its inverse, it should necessarily be equal to I, isn't that? So this is the property is that is going to be deployed in your finding inverse of a matrix by Gauss-Jordan method. Okay, right. Two rows equal, well, we have seen determinant equal to 0. And then if you swap, if you interchange the rows, you get a minus sign, right? And we have seen determinant A is determinant A transpose. And then R1 is done some row elementary operation by multiplying by any constant C, then it is C times the determinant A. The constant into determinant A. Then here, orthogonal matrices. When will you say a matrix to be? And this, of course, has nothing to do with this topic here. This is something is projected here, which has nothing to do with this property. Just look at, so ignore it. This, just look at this. This is very important definition that you can think of. A matrix A is said to be a square matrix. Of course, any special matrix should necessarily be a square matrix. A matrix A, a square matrix, is said to be an orthogonal matrix, if and only if its transpose is the same as its inverse. If the transpose and its inverse are the same for a matrix, then we say that such a matrix to be called as an orthogonal matrix. Clear? And you can find such an orthogonal matrix, its determinant value to be either +1 or -1, which you can verify. Okay. Now, rank in terms of determinants. We have already seen rank of a matrix denoted by usually small r or row by defining as number of non-zero rows after reducing it in an echelon form. Now, similarly, you can also find rank of a matrix using determinants. Now, what does the theorem say? What is in practice? How do you do it in practice? Consider an m by n matrix A equal to AJK. J rows, number of rows K, number of columns. J equal to 1 to etc. M, K equal to 1 to etc. N. A has rank R greater than or equal to 1 if and only if A has an R by R submatrix with a non-zero determinant. The determinant of any square submatrix with more than R rows contained in A, if such a matrix exists, has a value equal to 0. Now, what is the meaning of this? Very simple. Suppose you have a matrix of order 3 by 3. Okay, find its determinant. What do you mean by finding rank in terms of determinants? Find its rank determinant. If it is non-zero, then its rank is 3. Number of rows determines the rank of the matrix when its determinant is non-zero. When its determinant is non-zero. Okay, then remember we find the rank of the matrix through determinants. So here, suppose your determinant of A, where A is of order 3 by 3 equal to 0. See what's the meaning of this? What all these things are talking about? The determinant of any square submatrix. What's the meaning of this? Suppose you have determinant A is equal to 0. And of course, A is of order 3 by 3. Okay, and its determinant is 0. So one thing is very clear that the rank is not 3. So what does this imply immediately? Rank, this implies that R of A, R of A, R of A is not equal to 3. R of A is not equal to 3. So it is less than 3. Is it equal to 2? For that, you can take any square submatrix. Once the order of the matrix, when the element, the A is of order 3 by 3, you can take any. Now, no minor, no cofactor, not like that. You just take cofactor, we will come again. There is going to be an occasion where we will be coming back to cofactor, especially when you are going to find at the end inverse of a matrix, okay, using determinants. Okay, now, so here it is, you just take, for example, you have a 3 by 3 matrix. Now its determinant equal to 0 means the rank is not equal to 3. So you go for any square submatrix of order 2 by 2, isn't it? So naturally, when you take a submatrix, it will be definitely of degree 2. Now you have how many possibilities are there? You have first row, you have second row, you have third row, isn't it? You have first column, you go second column, you go third column. So you can have a submatrix of order 2 by 2, taking only this square submatrix. Find out its determinant. If it is 0, don't come to the conclusion that rank of A is not equal to 2, because you may be able to go for another submatrix of taking this square submatrix whose determinant is non-zero, or this, or this one. So even if there is at least one square submatrix, definitely which will be of the order 2 by 2. And if its determinant is non-zero, then that gives the rank of A to be 2. And if there are only 4 possibilities for a matrix of order 3 by 3. There can only be 4 square submatrices, each of order 2 by 2, isn't it? If all of them give determinant value 0, then you just declare that rank of A is equal to 1. So the minimum value of the rank is 1. Rank of A will be 0. Rank of A will be 0 only when if the matrix is a 0 matrix, not otherwise. Therefore, minimum rank is 1. So even if you are not able to get any square submatrix of reduced order and each of them is 0, you just declare therefore rho of A is equal to 1. Otherwise, by just taking one square submatrix whose determinant value is 0, don't come to the conclusion that R of A not equal to 2. If this is not the possible, you can go for taking the second one. You can take third one and go for fourth. Even if there is one, that's why if such a matrix exists, even if there is one square submatrix of order 2 by 2 exists, in the sense whose determinant is non-zero, then the rank of the given matrix is 2. As we said in the beginning, a n by n square matrix A has rank n if and only if determinant A not equal to 0. Suppose your original matrix A of order 3 by 3, whose determinant is not equal to 0, then the rank itself is 3. If it is equal to 0, the rank is not 3, then you have to go for searching its square submatrix existence whose determinant is non-zero. Have you got this one? Is it clear? Is it clear? Anyone? Varsha? Hello? Hello?
Yes,
Is this
yes,
point clear? Is it clear? How to find determinant, rank of a matrix whose through determinants? Is it clear?
yes, sir.
Shall we proceed? Okay. So here another one. Okay. Multiplication by scalar. Determinant of Ka is k power n into determinant A, not just k into determinant A. What's the meaning here? Determinant of Ka determinant of Ka is k power n into determinant A, not k into dt. I think this is confusing you. We said in the beginning, multiplying any row or column elements by a constant, and then if you do the expansion, you will just get C into determinant A. So naturally, you will feel like K into determinant A. It is not the case here. It is determinant of Ka means each row or column is being multiplied by a common constant K. Each row. So in that case, it is not just K, it is K power n if A is of order n by n. If suppose you have, for example, I think there is time is running out. So if we find time, then I will come back to it and I will show you this. So when you have a determinant, when you multiply it by K by a constant, say 2 or 3 or -1 or -2, throughout, that is every element of the element A. That is the meaning of your Ka. Not K being multiplied by any one row or column. So look at the difference. Multiple of a row by a constant K gives you the result K into determinant A because it is only in one row. But when you say determinant of Ka, it means K being multiplied by every element of that matrix. So what is happening then? If there are 3 rows, naturally you will get K power 3. That's the meaning. So these results are useful in answering your quizzes. All these properties will be of great use to you to answer your quizzes. Okay. So determinant of Ka is K power n determinant A, but not just K into determinant A. K into determinant A is possible only when K is a multiple of any one row or column. Hope you will be able to understand. If you want, I can give an illustration if time permits towards the end of it. Okay. We have to go forward. Cramer's rule. Well, this I don't need to enunciate again. Already you were exposed to this in the last session, but still, I would like to just show you an example again here by taking a 2 by 2. So here is a question just to have a recapitulation. Because since we have been discussing about determinants, its uses, its properties, and finding rank through determinants, we'll also once again check to solve system of linear equations. Maybe according to your scope, 2 equations in 2 unknowns, or at the most 3 equations in 3 unknowns. Okay. So here is a question to solve by Cramer's rule. So there is a system of 2 linear equations in 2 unknowns x and y. So how we are going to solve by Cramer's rule? Remember, you should read the question carefully. You should not, because solving system of linear equations can be done by many ways. Okay, by Gauss elimination method, by ordinary elimination and back substitution method. Okay, all those things are there. But when you are asked to solve by Cramer's rule, or sometimes they may even ask you to solve by using determinants. Using determinants leads to the conclusion that you need to solve by Cramer's rule, because Cramer's rule involves usage of determinants. So sometimes instead of explicitly giving you the tag as solve by Cramer's rule, so don't be under the impression that Cramer's rule word is not there. By determinants means you have to solve by Cramer's rule. So you need to first find D, the determinant of what? A. What is A? Matrix of coefficients. What is matrix of coefficients here? A. Matrix of coefficients. Isn't it? You need to find determinant of matrix of coefficients. That is D is equal to determinant A. Determinant A. That is 2 minus 4, 5, 2, which is nothing but is equal to 4 plus 20, 24. Isn't that? This is the first step. Then you need to find D suffix x to find the value of x as a dx by d, or dy next and dy, the determinant, then divided by d gives you value of y. Of course, this author uses, instead of dx, dy symbols, d1, d2. So it is shown on the next slide that you can see. D we already find 24. D1. What is D1? Or dx. That means the first column of D must be replaced by the constants on the right hand side. Isn't it? So go look forward to the constants on the right hand side. Minus 24, 0 becomes the first column. Second column of in the D, minus 4 minus 4 2 remains as it is. So now that is how you are getting your determinant 1. That is determinant x. Means what is the meaning? This is nothing but coefficients of x. Isn't that? Just look at in the equation, system of equation. 2, 5 forms a column which are nothing but coefficients of x. That's why the first column is being replaced by the constants. Okay, in the column sense. So you now expand minus 48 minus 0, so you get minus 48. Then d2 or dy is obtained by changing or interchanging, not exactly interchanging, by removing the second column, namely the column of coefficients of y by constants. Okay. So you are replacing, exact word, replacing the second column, namely y coefficients column, by the same constants. Again, you are going to use only the constants. Minus 24, 0 became the first column for D1. Minus 24, 0 becomes the second column for your finding y by replacing the second column now. So 2, 5, the first column remains the same, and minus 24, 0, you got the second column replaced by constants. So 2 into 0 minus of minus plus 24 into 5, 120. Supposing you have 3 by 3, you will find D3. So the same way, by retaining first and second columns as they are, you will replace the third column, namely the coefficients of Z column, by the same. constants. Okay, so you will get D3. In that sense, you will get x equal to d1 by dt, y equal to d2 by d, sorry, d1 by d, d2 by d, d is the same, and d3 by d. That's all. So here is being a 2 by 2 because you have only to solve by Cramer's rule a system of two linear equations in two unknowns. So x is d1 by d, y is d2 by d. What is d1? 120. What is d? 24. So d1 is minus 48, d is 24, so it is minus 2. And y is d2 by d, that is 120 by 24, which is 5. So the solution is minus 2 comma 5. Or you can write x is equal to minus 2 and y equal to 5. And you know very well, always it is better to check the values that you have obtained are correct or not by substituting in the left hand side of any one of the equations given. So you have minus 2 and 5 to be the solutions. That is x equal to minus 2, y equal to 5. You substitute in the left hand side 2 into minus 2, minus 4. Minus 4 into 5, minus 20. So you get minus 24 right hand side. So left hand side equal to right hand side means x and y values satisfy the equation. Similarly, you can check the other one also. In fact, it should say satisfy all the equations. If there are two, both the equations. If there are three, all the three equations must be satisfied. But it is enough if you check with any one of them. Naturally, it will satisfy the other equations also. So that for this problem, the solution is x equal to minus 2 and y equal to 5. Similarly, you can solve by Cramer's rule the system of given system of three linear equations in three unknowns by finding d1, d2, d3, and also originally finding d, then d1, d2, d3, and then x equal to d1 by d, y equal to d2 by d, and z equal to d3 by d. And finally, after getting the calculations done, you substitute for x, y, z in any one of the equations. Any one of the equations, it's enough. If you take the left hand side, substitute the values of x, y, z, and see that it is equal to the right hand side. Now, inverse of a matrix. As I mentioned sometime back, AB equal to BA equal to I means B is the inverse of A. In the sense, A into A inverse is I and A inverse A equal to I. This is something like what? X into X inverse equal to 1. X inverse into X equal to 1. 2 into 2 inverse equal to 1. 2 inverse into 2 equal to 1. You have in the matrix parlance, a matrix multiplied by its inverse is I. Okay. Remember, A inverse is not your 1 by A. There is no division of matrices. Inverse binding is different and it exists only for a non-singular matrix. That is a matrix whose determinant is non-zero. Right. The inverse of an n by n matrix A is denoted by A power minus 1. But don't read it as A power minus 1. Read it as A power A inverse. Is also an n by n matrix such that A inverse is equal to I. But I is the n by n matrix, which is nothing but the unit matrix. Suppose you have a matrix of order 3 by 3, then A inverse will also be of order 3 by 3, and I is your unit matrix of order 3 given by 1 0 0 0 1 0 0 0 1. Again, remember that for the unit matrix, only the principal diagonal elements are 1 each. Principal diagonal elements are 1 each. Other elements are zeros. So if A has an inverse, A is called a non-singular matrix because it is possible only when determinant A is non-zero. So it is non-singular matrix, otherwise singular matrix. If determinant is 0. Okay. Just see that if such an inverse exists, it is unique. What do you mean by unique? It is one and only one. That means, how will you prove it? If at all there is another one, they are one and the same. That means there is only one and only one. That's what we say here. If A has an inverse, the inverse is unique. Indeed, in fact, if both B and C are inverses of A, suppose we say that there are two inverses. It cannot be. Suppose you say that there are two. Then what will happen? They are nothing but one and the same. They cannot be two different. They should be one and the same. That we are trying to prove. Then, okay, if suppose B and C are inverses of A, what will happen? If B is inverse of A by property, what is AB? I. AB equal to I. Similarly, since C is inverse of A, CA is also I. Okay, right. So, since we have taken, if possible, or if B is an inverse of A, we know AB equal to I. Since C is also contemplated to be an inverse of A, CA equal to I. Okay, but we are trying to prove that they are not different, but they are one and the same. How? Just see. So start with the B. Okay, we are trying to prove now B equal to C. B equal to, how we can write B? Any matrix multiplied by its unit matrix is the same, isn't it? That's why a unit matrix is called a multiplicative identity matrix. Something like X equal to 1 into X. In matrix, any matrix is matrix multiplied by its unit matrix. So B is IB. Okay. Now, I can be written as CA because I am bringing in. You may ask one question. Is it not I equal to AB? Again, we don't want to go for AB because we started with B. So we need to bring in C. So I can be replaced by CA because C is assumed to be an inverse of A. So CA is I, property is made use of. Now, associative property is possible for multiplication of matrices. CA into B is same as C into AB. But then, since B is inverse of A, what is AB equal to I? CI. But what is CI again? By multiplicative identity property, C. And thus, we started with B and going through the properties, we are able to end up with saying that it is equal to C. So, there cannot be two different inverses. So, it is unique. Have you got this point? It's an important point to ponder. Anyone? Any feedback? Okay, fine. Got it. Right. Now, existence of the inverse, that's what we have just checked. Now, cancellation loss. What's the meaning of cancellation loss? That A, B, C, B, n by n matrices. Then, if rank A equal to n and AB equal to AC, then B equal to C. So, you are able to, this is called a left cancellation. So, you are able to cancel A on both sides, being multiplicative with the other two matrices. Remember, which is possible one only when all of them are of same order and rank of the common matrix is the maximum order number. So that is important. If rank A is n, which is the order of each of the matrices, such that AB equal to AC, then B equal to C. If rank A equal to n and AB equal to 0, naturally implies B equal to 0. Hence, if AB equal to 0, but A not equal to 0, as well as B not equal to 0, then rank A will be less than n and rank A, B will also be less than n. Right. If A is singular, then AB and BA are also singular. Because if A is singular, then determinant A equals 0. So any matrix whose determinant will be multiplied by 0 get 0, so they are also singular. Now, this is what exactly the final topic of the day, an important one. Inverse matrix by Gauss-Jordan elimination method, or simply Gauss-Jordan method, as it is named after the two famous mathematicians, Gauss-Jordan. So what is Gauss-Jordan method? Remember, as I have been emphasizing this fact that find the inverse of a matrix. If the question is there, well, you are at liberty to find inverse by the usual method that you may be aware, which you have studied in your school days. Nothing but 1 by determinant A into adjoint A. Where determinant A is provided determinant A not equal to 0. Is all you got studied. Or if it is emphasized that by using determinants, this is the formula. If nothing is prescribed, this is the formula you can use if you want, because that will be easier going by determinants. And if it is by determinants, well, again, it is simpler, the same. But mostly according to your scope, as you are now being exposed to a new concept of finding inverse, apart from the one that you are already familiar with, namely Gauss-Jordan method, which is nothing but going to be an elimination, or rather reducing it to an echelon form of an augmented matrix AI. Rather elementary row operations, which we're doing it uniformly. So to solve a system of linear equations, you have seen the augmented matrix AB, where A is matrix of coefficients and B is the matrix of constants, that is constant vector. AX, AB. So when R of A equal to R of AB, you have said at equal to N, system is consistent and it has a unique solution. If R of A equal to R of AB, system is consistent, but if the rank is less than the number of unknowns, then it has infinitely many solutions. If R of A not equal to R of AB, system is inconsistent in the sense the system has no solution. So these are all useful results to be remembered, can be used for answering quiz questions. Now here, the same way you are going to not just reduce as you have found for rank of AB, the augmented matrix. Here we are going to find not rank, but we are reducing it to echelon form of the augmented matrix AI. A is the matrix of coefficients. Here we don't need to say even matrix of coefficients, because it is not the coefficients of x, y, z or xy in the system of equations here, because it is only the matrix A, which is AJK or AIJ, A11, A12, etc. Whatever is given in your question. Then you have I. Here is an example. To find the inverse of a matrix using Gauss-Jordan method, where A is, of course, here you are given a 4 by 4 matrix. A11, A12, A13, A14, etc. What is augmented matrix? The bar stands for augmentation. That is, you are taking elements of A, line, straight line, vertical line, elements of I. Okay. So here, unlike in AB, where you had their matrix of coefficients, that is A matrix, you can simply say A matrix. And here you just had only a column vector, that is a matrix of constants only. But here it is again a matrix which is also of order same, 4 by 4 here, according to this illustration, which will be therefore, remember, I think for the first time you are seeing this 1, 0, 0, 0. So naturally the principal diagonal element 0, 1, 0, 0. Next one 0, 0, 1, 0. And next one 0, 0, 0, 1. But most practically you will be having finding inverse of A of order 3 by 3. Anyway, it is going to be an extension. So whatever you do to left hand side, do to the right hand side, as you used to do for any augment matrix that you have already seen. The same thing. Whatever you have done for the left hand side, any row elementary operation is same to be carried out to the right hand side also. Okay, useful. Okay, this idea already I just have talked about, useful when solving system of equations also, which you are already familiar with. So AI, elementary row operations, ERO is nothing but elementary row operations, leads to, implies that you get another matrix now. Finally, after doing a few steps of elementary row operations in such a manner that you reach a stage where you have again an augmented matrix, but this time you have 1, 0, 0, 0, 1, 0, 0, 0, 1 if it is of order 3 by 3. Then you have the augmentation, some matrix. Definitely because of elementary row operations, you must only ensure that you are doing the elementary operations systematically until you reach the first portion to be the I, and second portion naturally there will be a 3 by 3 or 4 by 4 matrix. And that is the matrix required. And that is the matrix inverse of A. So that is the step cut. It's already 5:25. Shall we have a break for 5 minutes and then resume? Hello?
Sure, sir.
Okay, right. Hello? Are you ready?
Yes,
Hello?
sir.
Yeah.
Okay, fine. So let's find now inverse of the given matrix A by Gauss-Jordan method and Gauss-Jordan elimination method. That is, we are going to reduce it to echelon form in the sense we are just going to have elementary row operations leading to the augmented matrix AI originally taken, resulting in I in the first part, so that you have another 3 by 3 matrix, and that is the required inverse of the given matrix. So given A minus 1, 1, 2, 3, minus 1, 1, minus 1, 3, 4. So let us take the augmented matrix AI. So you have the matrix symbol, you have the matrix A, and put the vertical line and write the elements of I, because this is being 3 by 3, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1. Now, you know very well, as if you are reducing in the echelon form, first thing you will do, because you need to have, remember, keep in mind, the first portion should become 100, 010, 010, 001. Therefore, as you do normally always in any elementary row operation, go for the second row first column element to become 0. So keep the first row as it is now. So that is actually here row 1 is row 1. So if at all you want to put it as a symbol, normally we write this way. R1 is R1. Okay, R1 is R1. So R2, coming to R2, you have 3, this should become 0. The revised, the new second row should become with the first column element 0. So how will you get it? You, since this is fixed, you have to have a correspondence between R2 and R1 from the existing one. So when we look at 3 plus 3 into minus 1, isn't it? So that means R2, you are going to be the new R2 is obtained by the existing R2. See, this is what exactly we mean by row elementary operations. You have to be careful about this plus 3 times R1. When this portion to become, this element to become 0, you have to check. And the same is to be done throughout the row. Okay, so row 2 is actually row 2 plus 3 times row 1. That's the meaning, isn't it? Row 2 plus 3 times row 1. Okay, right. So 3 plus 3 into minus 1, 3 minus 3 is 0. Minus 1 plus 3 into 1, minus 1 plus 3, 2. 1 plus 3 into 2, 1 plus 6, 7. And you have to do it on the right hand side also. Okay, don't forget. 0 plus 3 into 1, 3. 1 plus 3 into 0, 1. 0 plus 3 into 0, 0. Similarly, you have to perform row elementary operation on R3, keeping R1 fixed. So one set of operations, you have two operations. One is R2 in terms of R1 and R3 in terms of R1. So as to make the first column, second row 0, and first column, third row also 0, isn't it? So here you go minus 1, here you go minus 1. So how will you get this element 0? If you subtract. So you need to get R3, new R3. So this R3 minus R1, because minus 1 minus of minus 1, you get minus 1 plus 1, 0. So third row, new R3 is going to be obtained by the elementary operation of existing R3, that is row 3, minus row 1. So minus 1 minus of minus 1, 0. 3 minus 1, 2. 4 minus 2, 2. 0 minus 1 minus 1. 0 minus 0, 0. 1 minus 0, 1. So one set of operations which you normally do has taken place. Now look at it's the same way. Second set of operations. This is what normally you do when you do finding rank of A only or rank of the augmented matrix A. Isn't it? So the second operation is that is one set, both of R2 on R1 and of R3 on R1. That is one set. And in the second set, you have only one operation. That is, you need to have now third row, second column element is also becoming 0. So this time what you have to do, having done both operations of R2 and R3 with R1 fixed, now R2 is also standardized, isn't it? R2 is also fixed, standardized. So you can keep R2 as basis now. So here R1 is R1. 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 R2 is R2. So let us go for now R3 in terms of R2. So for that you take R3 existing. Here you have 2, it should become 0. You have to do the elementary row operations of R3 on R2. Okay. So it is 2 minus 2. So how will you get? It is 2. Here is 2. So it is simple. R3 minus R2 will be 2 minus 2 will get you 0. That is R3 minus R2. Simple. So 0 minus 0, 0. 2 minus 2, 0. 2 minus 7 minus 5. Minus 1 minus 3 minus 4. 0 minus 1 minus 1. And 1 minus 0, 1. So thus we have done 2 sets of operations as usual. So hereafter, what's happening? This is what going to be an extension. Look at now minus row 1. What's the meaning minus row 1? Just go back. Now we just look at, we keep an eye on the first portion becoming a unit matrix. So the first element should necessarily be 1. You have minus 1, isn't it? So what is the meaning? Either you multiply by minus 1 or you divide by minus 1, isn't it? So here it is given first row being multiplied by minus. So minus into row 1, minus 1 into row 1. So it gives you plus 1, minus 1, minus 2, minus 1, 0, 0. Just see. Sorry. Minus 1, I mean plus 1, minus 1, minus 2, minus 1, 0, 0. So the existing row multiplied by minus 1 gives you this one. So that the first row, first column element has become now 1. Okay. Now whatever we have done for the first row, first column, second row, third row elements, now we do it in the reverse order. That is what we do next. You just look at, before you do any elementary operation, just look at the second row here. You need to have 0, 1, isn't it? 0. Of course, these are all going to be zeros as we have done elementary row operations for first row. We are going to do for the first column. We are going to do for third column, isn't it? Okay. Now from the top. Now from the second, we have to go to here first second row, then third row. Here we are going to go second row, third column, and then first row, first column in the reverse order. Okay. But before that, we can also do one thing here. You can make this as 1 by dividing the second row by 2 or multiplying by 0.5. Both are one and the same, isn't it? So here it is given 0.5 into row 2. So what's happening? 0, 2 into 0.5, 1, 7 into 0.5, 3.5, 2 into 0.5, 3 into 0.5, I mean, yeah, 1.5, then 1 into 0.5, not 1 into, yeah, 1 into 0.5, that's 0. Okay, and similarly, what you are having in the third one, see that's not written here. So third one also we can do that way. You just see that 0, 0, 1 you should get, isn't it? So you can multiply by point, divide by minus 5, isn't it? Divide by minus 5 or multiplied by, you divide by minus 5. Okay, so you get 1. So next you get minus 4 divided by minus 5. So 0.8, something like that. So you know how to do that. Okay, simple. So you get this way. So that you are having 1 something, 0, 1 something, 0, 0, 1. So our aim is to now have this is made 0 and this is also made 0. This is also made 0, isn't it? So we go to first row. Now what we did, row 2 and row 3 in terms of R1 we did. Now the other way around. Row 2 and row 1 we will do in terms of row 3. Row 3 is fixed because just look at row 3, 0, 0, 1. It is fixed now. So there is a network issue. Right. Now row 1 is now row 1 plus 2 times row 3 is that is row 3 is row 3. So row 1 you have minus 2, row 3 you have 1. As you have done for the first column, you have to now do for the third column. Okay. Either you can do first, second row and then first row, or you can start from first row itself. Nothing wrong. Anyway, you need to make them 0. Okay. So first row plus 2 times third row. So minus 2 plus 2 into 1, you get 0. Here also you can check 1 plus 2 into 0, 1. Minus 1 plus 2 into 0, minus 1. They will not be changing. If they are getting changed, then somewhere you have gone wrong. Okay. So you have to be clear. So here, next is 0 plus 2 into 0.2. So you get 0.4. 0 minus 2 into 0.2. 2 into minus 0.2. So you get minus 0.4. Similarly, in order to make this second row, third column element also to be 0, keeping same R3 fixed, you have to do for R2 on R3. So how will you go do 3.5? This is 1. So 3.5, next step. 3.5, that is row 2 minus 3.5 times row 3. So 3.5 minus 3.5 into 1, you get 0. 1.5 minus 3.5 into row 3 into 3.5 into 0.8. So you get minus 1.3. Similarly, you have to do these things. You get second row. So thus you are having 1 minus 1 0, 0 1 0, 0 0 1, etc. on the right hand side. Now, what is happening now? This you must have 1 0 0. So now, as you had done in the first part, 2 sets of operations. Now you need to have 2 sets of operations in the second part. So one set of operations of doing R1 and R2, keeping R3 fixed is over. So one more is remaining, isn't it? That is your R1, isn't it? R1, keeping R2 fixed because R2 is now fixed. So go to R1. So this is minus 1, this is 1. You must get 0 here. So what will you get? R1 is R1 plus R2. So 1 0 0. Here 0.6 minus 1.3 minus 0.7, 0.4 minus 0.2, 0.2 minus 0.4 plus 0.7, 0.3, and remaining will be 0, 1, 0, minus 1.3, minus 0.2, 0.7, 0, 0, 1, 0.8, 0.2, minus 0.2. Now look at this. What's happening here? So what we have arrived at now? This is equal to matrix, augmented matrix, I. There is some matrix, and that is the required inverse matrix. Got it? And therefore, what is required is this is the required inverse matrix. So you must be able to reduce it in such a manner that AI should become I something. That something, the resulting matrix is nothing but your A inverse. Now, I would suggest to you to check whether your inverse matrix is correct or not. What you can do, take your original matrix A given, and the resulting matrix A inverse, multiply them, what you must get? I. If you are getting 1 0 0 0 1 0 0 0 1, if it is of order 3 by 3, then you are correct. Okay. Is there any doubt here? Anyone? Hello? Is it clear? Thus, AI reduced to IA inverse using row or column operations. We do row operations. Okay. So here, two questions. Find the inverse of a non-singular matrix. So inverse you can find only for non-singular matrix by Gauss-Jordan method. Here is a 2 by 2 matrix and here is a 3 by 3 matrix. As in fact, though it is given example, you can take it as practice problems. You can try yourself. If time permits, I think I have done one of them. I will show you. I have done for you. Yeah, I have done. Is it the same? -1, 1, 2. Just check. 3 minus 1, 1. Yeah, it's the same. It's the same. So just for 2 by 2, you can find out, you can check easily. And that's, you know very well this. A inverse is, it straight away come to this. A inverse is 1 by determinant A into what is the CJKT or transpose at, in fact, this can be regarded as, AGA. AGA means adjoint of matrix A. What is adjoint of matrix A is nothing but, if you just look at this, just read it, transpose of CJK. Some matrix superfix T means transpose of. What is CJK? Cofactor matrix or matrix of cofactors. Okay. So what is this C11, C21, etc., CN1, C12, C22, etc., etc.? What is the meaning? First row, first column, second column, first row, nth column, first row. First, this is first column, second row, second column, second row, nth column, second row, and so on. So you have, it is the matrix of, this is actually transpose. Originally, you will have C11, C12, C1n only, isn't it? So this is transpose. You know what is transpose? Interchange of rows and columns. Therefore, here, where CJK is the cofactor of AJK in determinant A. So here, cofactor means you will find cofactor of every element of A. And in for that, now you are going to see, you get exposed to, just see that. Look at this. Find the inverse of a matrix. So when the question is, as I told you in the beginning, if there is no tag, if there is no insistence that find the inverse of A using Gauss-Jordan elimination method, you are at liberty to use determinants. Okay. So which is 1 by determinant A into adjoint A. What is adjoint A? Transpose of matrix of cofactors. What is a matrix of cofactors? Matrix formed of elements of cofactors of each of the elements of A. How do you get it? Just say that. So what is determinant A? -1 into -4 -3 -7. That is -1 into -1 -1 into -7. Then -1 into, this is 12 plus 1, 13. Plus 2 into 9 minus 1, 8. So you get the answer 10. So determinant of the given matrix A is non-singular, not equal to 0. So we can go for finding its inverse. For that, as I said before, you need to find cofactor of each of the elements. So C11 means cofactor of -1. Remember? Cofactor of -1. First column, first row, first column element, which is nothing but the remaining determinant. Okay, but here, what is important for minor, it is just the expansion of the determinant only. But for cofactor, you have to the sign must be preceded here before the minor. That's why you got there -1 power j plus k. So before the minor, you have the sign. That sign is nothing but positional sign of the element for which you are finding the cofactor. So here, don't put minus here. It is you are finding cofactor of -1, whose positional sign is plus. And so on. So plus of what is a minor? -1, 1, 3, 4. So you get -7. Then what is C12? First row, second column. What is positional sign? Look at minus. Now we write its minor. Don't multiply that element. That is only for expansion. And that is only through any row or a column. But for cofactor, you have to find cofactor for every element by its minor and assigning before the minor, that is the 2 by 2 determinant, you have to have the sign, positional sign of the element for whom you are finding, for which you are finding the cofactor. So it is minus of 3, 1, -1, 4. You get -13. Then C13, first row, third column. It is plus of, what is its minus? 3, -1, -1, 3, which is 8. Similarly, C21, C22, C23, C31, C32, C33. Therefore, A inverse is, formula is, A inverse, formula is 1, determinant A, adjoint A. Where adjoint A is transpose of CJK. That is matrix of cofactor. That's the reason why, just look at here. You may be wondering that you are getting, of course, straight away the answer is given because determinant A is 10, that is 1 by 10, isn't it? This is equal to 1 by 10 actually. 1 by 10. Then you have the matrix of cofactors of transpose of cofactor. Okay, so what will happen? What you should have got actually C11, C12, C13. That is the first row. C21, C22, C23. That is the second row. C31, C32, C33. That is the third row. Isn't it? So transpose means C11, C12, C13 will become the first column. C21, C22, C23 will become the second column. C31, C32, C33 will become the third column. So straight away, that's the reason why it is calculated like this as a column. Since we are going to take later on the transpose, we are straight away writing, just look at -7 by 10, minus 0.7. Minus 13 by 10 minus 1.3, column wise. 8 by 10, 0.8. 2 by 10, 0.2. Minus 2 by 10, minus 0.2. 2 by 10, 0.2. 3 by 10, 0.3. 7 by 10, 0.7. Minus 2 by 10, minus 0.2. So this is how we get the inverse of the given matrix using determinants. So finally, diagonal matrix. So what is diagonal matrix? Only the principal diagonal elements will exist. And all remaining elements should be 0. So diagonal matrix is a matrix whose diagonal elements do exist. Well, not all of them are zeros. If all of them are zeros means diagonal elements are also zeros means it becomes a zero matrix. Therefore, at least there can be a zero in the principal diagonal elements also as an element, but not all of them, isn't it? But practically, suppose you have a 3 by 3 matrix or 4 by 4 not, you will have at least non. In fact, all of them are non-zeros, principal diagonal elements, and maybe 1 0 might be there, but it should be non-zero anyway. Okay, so diagonal matrices J not equal to K, AJ K equals 0 have an inverse if and only if all AJJ not equal to 0. What is AJJ? A11, A22, A33, A44, etc., ANN. Or if it is a matter of matrix of order 3 by 3, A11, A22, A33. Isn't it? So they are not equal to 0. So principal diagonal elements are all not equal to 0. Okay. So that is very important now. So all AJJ not equal to 0. Then only diagonal element matrix has only diagonal principal diagonal elements. It can have inverse only if those principal diagonal elements are all non-zeros. Okay. And what will be the type of its inverse? It is also diagonal. That means only principal diagonal elements will exist to be non-zeros. And what will be what the elements will then be? It is nothing but the reciprocals of the entries of the original matrix. Okay. So A inverse is also diagonal with entries 1 by A11, etc., 1 by ANN, 1 by A11, 1 by A22, 1 by A33, and so on. So this is how diagonal matrix has inverse only when principal diagonal elements are not all of them are non-zeros. Now, this is a simple example. Inverse of a diagonal matrix. Given A, then we obtain the inverse A inverse by inverting. That is by taking each individual diagonal element of A by taking 1 by. It's reciprocal to be diagonal elements. So A inverse will be 1 by minus 0.5. That is minus 1 by 1 by 2, which is 2. Minus 2. 0 by 0, 0, 0, 0. And only principal diagonal elements. Isn't it? 4 divided by, 4. It's reciprocal 1 by 4. 0.25. Or you can write 1 by 4. Then last one, 1 by 1, 1. So you go 1 by minus 1 by 1 by 2 or minus 1 by minus 1 by 0.5, you go minus 2. 1 by 4, 0.25 and 1 by 1. So A inverse is also diagonal and all its principal diagonal elements are non-zeros. Okay. Why? The insistence that all AJJ, that is A11, A22, A3 must be non-zeros is that supposing there is a 0. So for example, this is 0. Then if you take the reciprocal, it will become 1 by 0, which is infinity, isn't it? Which cannot be the case. Therefore, necessarily, DI must be non-zero elements. Then only the inverse exists. Practice problems. Okay. For example, if you take this determinant, you know how to expand a 2 by 2 determinant. Sin alpha, cos alpha, sin beta, cos beta. What is its expansion? Cos alpha, cos beta minus sin alpha, sin beta is the immediate answer. But of course, you can have a simplification of this if you know trigonometric formulae of compound angles. Can anyone say what is cos alpha, cos beta minus sin alpha, sin beta? Anyone? If you are able to recollect trigonometry and sine cosine of compound angles like sin of A plus B, sin of A minus B, cos of A plus B, cos of A minus B, something like that.
Cos of A plus B.
Very good. That's right. May I know who has given the answer?
Apurv.
Atul.
Apurv.
Okay,
Apurv.
fine, good. So cos alpha, cos beta minus sin alpha, sin beta is cos of alpha plus beta. Good. So similarly, 2 by 2 we can find. And of course, here also you have one result. This is a hyperbolic. This is a circular trigonometry function. This is your hyperbolic. If you are able to remember, you can give this answer also. If you remember, this is cos ht into cos ht, isn't it? Cos h square t minus sine h square t. What will be the answer? For circular trigonometry function, cos square t plus sine square t is 1. But for hyperbolic function, cos h square t minus sine h square t, are you able to recollect? Is
No, sir.
cos h2t, cos h2t. Okay,
Okay.
something like that. Okay, right. So you can, how to. So now here, of course, very simple. This is being upper triangular matrix. Its a expansion will be 4 into 2 into 5. Principal diagonal elements product, that is 40. You can check other elements. So you have some more problems, practice for example problems. Find inverse of a matrix using Gauss-Jordan method. Mostly, since this is new to you than what you have studied in school days, finding inverse through determinants, that is using the formula A inverse equal to 1 by determinant A into adjoint A. You may definitely be asked, since it is new to you, the concept of finding inverse of the given square matrix using, inverse of a given matrix using Gauss-Jordan method by making them from AI to IA inverse. So if there are any queries, I can answer. And as I told you in the beginning, that when you have this determinant of Ka is equal to, it's not just K into determinant A, but it is K power n determinant A. You can easily check that. For instance, suppose, shall I just demonstrate to you if you want?
Sure. Sure, sir.
You want me? Okay. Let me just see determinant A. Is equal to -1 -3 -2 6 1 0. Okay. So well, now you can easily find its value -1 into 0 plus 2. So 2 minus 2 into 0 plus 12 plus 4 into -3 minus 30 minus 33. So that its value is -1 to, is it? Yeah, not this one. I'm just taking now determinant Ka, not A. I just take determinant Ka, isn't it? And I take K is equal to 2. So I take determinant 2A. So this is A. Then I find, of course, determinant 2A. Determinant 2A means it is actually so this means determinant every element is multiplied by 2. Minus 2, 4, 8, minus 6, 10, 4, then 12, 2, 0. This is minus 1. And this expansion actually, this gives minus 1264 minus 1264.
So the writing thing is not visible for us actually.
Oh, okay. So this is, see, 2 times I have multiplied, okay, determinant Ka where K equal to 2. So you go minus 2, 4, 8, minus 6, 10, minus 4, 12, 2, 0. So if you simplify this, you get minus 1264, minus 1264. So this is same as 2 cube into, so it is same as 2 cube into determinant A. That is actually, it can be checked now. We have seen already. So it is now 8 into 2 cube is 8. And determinant A is minus 158. Which is same as your minus 1, 2, 6, 4. So you are able to see that determinant 2A is equal to not just 2 into determinant A, but it is 2 cubed into determinant A in this case, because 3 is the order of the matrix. So in general, determinant K is equal to K power n into determinant A when n is the order of the matrix. So whenever you have every row or column is multiplied by a common constant, then it is not just K times determinant A, but it's a power where the power is the order of the matrix. Okay. Anything else? So it's already 6:15. If you have got any question, you can ask and clarify. Otherwise, I will stop sharing and conclude the meeting. Conclude the session. Anything else? Any doubt?
No,
any
sir.
clarification you want to see? Have you all understood it?
Yeah, sir.
Okay, then. Thank you then. Okay. Thank you.
Thank you, sir.
Thank you all.
Thank you, sir.